Welcome to segment 2 of in situ permeable reactive barriers. This time we're going to talk about a case history where we have an experimental permeable reactive barrier treating a mixture of petroleum hydrocarbons and chlorinated solvents. In the following segments we'll talk about other hydrocarbon-related experiences. The listing of the specific information for this lecture and the next lecture is provided here. So we're beginning to look at some examples of PRBs that I've had some involvement with. This case is a sequential PRB, that is, we have at least two treatments operating in sequence because we have two different contaminant groups, BTEX and chlorinated solvents, which are best treated by quite different technologies. Our intent was to treat the chlorinated solvents with a zero-valent iron treatment and to treat the hydrocarbons using a sparging technique in which we would maximize biodegradation. The sequential PRB is located in Alameda, California, at an abandoned or closed naval air station in Oakland. It's a very nice place. It's across from downtown San Francisco, and so quite often we have this beautiful view of downtown San Francisco from the field site. When we came upon the site, there was a few wells nearby, and that identified this as a potential place to demonstrate sequential treatment. The conceptual model that we ended up with when we first got to the site was as follows. We assumed there was some waste disposed inland a bit from where we were planning to put our sequential treatment system. We had a few wells around. The stratigraphy was fairly clearly defined. There was a sand unit that went down perhaps 20 or 22 feet, underlain by the bay mud, a very good aquitard. The sand unit, in fact, was dredged from the bay itself and appeared to be quite uniform and homogeneous, so an ideal place to try an experiment in remediation. So the initial part of the treatment was decided to be zero-valent iron to treat the chlorinated solvents. And again, as we discussed in the segment 1 lecture, we need to come up with some design. That is, we need to know something about the groundwater flow rate and the concentrations we could expect to try and design the zero-valent iron barrier component to adequately treat the contaminants. We had one fully screened well in front of the gate, and that was the basis for the design. In fact, it was the basis for the water that we tried zero-valent iron on. Groundwater velocity from hydraulic measurements in the area was about 6 centimeters a day. The water treatment objectives were the California MCLs for drinking water. We weren't really constrained legally to treat it to that extent, but that was our intent, to show that we could. So environmentals did a lab test for us. They determined that at 6 centimeters a day velocity that these contaminants could be treated with a zero-valent iron barrier that was 37 centimeters thick. That gave sufficient residence time for treatment. A conservative design was then chosen, as it almost always is, of 150 centimeters depth. Again, note the challenge. We're trying to take cis-DCE from 32,000 micrograms per liter down to 6. And vinyl chloride's even worse, 25,000 down to 0.5 micrograms per liter. So we designed and built the gate for those concentrations. Subsequently, when we installed multi-level wells around the gate, we found that there were some much higher concentrations. So here's a listing of the concentrations found in a multi-level well just in front of the gate, where you see that cis-12DCE is now almost 200,000 micrograms per liter. Vinyl chloride essentially 50 milligrams per liter, much higher than our design. So again, we now are a little bit worried. If that water moves directly through the zero-valent iron barrier, it really won't treat the contaminants to the level we expected. So we expect failure, unless there's some groundwater mixing and dilution that goes on in the gate. Hydraulically, that wasn't anticipated, and we'll see if we got it or not. Gate construction was quite interesting, a lot of big toys for boys. This shows a picture of the system under construction. The groundwater flows from right to left on this figure. We're constructing a funnel and a gate. In fact, we had two gates. The second gate was sort of an untreated gate to act as a control on the experiment. We won't talk about it. The construction was basically putting in sheet piling down into the aquitard. This is Waterloo barrier, a sealable sheet piling. It really is quite impermeable. Dewatering the sand aquifer, removing the sand aquifer in the gate, and replacing it with the material we wish to use. Here's the overall configuration of the gate as we constructed it. So the funnel is to the left and the right of the gate. The gate is open at one end and closed at the other end. This allowed us to control the flow rate through the gate. Our intent was to increase the flow rate if we were able to easily treat the ambient flow rate of 6 centimeters per day. We controlled the flow rate with pumping wells in the down gradient end. The material at the very front of the gate was a mixture of sand with a little bit of iron, sort of giving it a pre-treatment of iron. Then the 1.5 meters of zero-valent iron granules. Then gravel to separate that zone from the next zone. An open water zone was created, and we'll show you some pictures of it, in which we did some sparging, minimal sparging, with the idea of just adding a little bit of oxygen to promote aerobic biodegradation. Then we had a final gravel zone in which we could place monitoring. So again, water moving from left to right in this picture. We had the aquitard in front, then the sand with a little bit of iron unit, the zero-valent iron unit, gravel, the open biosparge zone, and more gravel. One concern at this site was that the water table would be fluctuating, and if it fluctuated such that it was now below the level of the iron, that might cause undue oxidation of the iron. So the idea was to keep the iron saturated. So we created a low permeability unit of sand and bentonite over top of the zero-valent iron. That forced groundwater to enter the gate by diving down in and moving through the gate. It also kept the iron from becoming aerated completely. Again, we pumped from fully screened wells at the end to create a velocity in the gate of about 6 centimeters per day. We put a cement base in for geotechnical reasons. It was viewed that the bay mud would be overloaded by this relatively small zone of very dense iron and would actually sink. So we had to put in a layer of cement to spread that load. And again, we were designing this for a residence time in the iron based on this 6 centimeters per day. The zero-valent iron was there to dechlorinate the chlorinated solvents, and the biosparge zone was really for aerobic degradation. Turns out that the less chlorinated solvents, vinyl chloride especially, is subject to aerobic degradation. So we might get rid of BTX and vinyl chloride in that last open water zone. So zone for treatment of the chlorinated solvents, and a polishing step, and an aerobic treatment of BTEX. An interesting construction detail, we wanted an open zone in which to do the biosparging. We could have put gravel in place and sparged, but as we heard in the previous lecture by Neil Thomson, unless the gravel is very coarse, we'll get channelized flow and not good contact between the residual air left in that zone and the groundwater that moves through. We decided that since this really was an experiment, we might want to replace what we had put in. And the easiest way to replace things was to leave the zone open. So we constructed a permeable barrier which allows water to flow through it, and as long as we had coarse gravel on either side of it, the gravel wouldn't enter into this zone. And that allowed us then to go down from above if we needed to replace things. In the bottom of that, we put in a biosparge tubing. This is just agricultural tubing used for drip irrigation. It's slightly permeable to gas, and when you put some gas pressure on the inside, you can see the bubbles appearing on the surface of the water. The idea was to minimally sparge this, just to give it a short shot to allow the system to become aerobic, leave it for a while, and then give it another shot of oxygen, just to make sure that there was always oxygen present. And that seemed to work quite well. In California, air quality is an issue, so we were asked to monitor the off-gas coming out of this system. We did so, and we never detected any of the hydrocarbons in the off-gas. So really, we weren't sparging, we were biosparging. The monitoring that was set up, we had multi-level wells with 3 depths, top, middle, and bottom, at the gravel unit just in front of the gate, then following the zero-valent iron, and then the biosparge zone with 2 fully screened wells in the down gradient end. Here was the concentration of 1,2 DCE, cis-1,2 DCE, early on in the experiment. You can see the concentrations coming into the gate are as high as 26 milligrams per liter. Concentrations were always quite low on this side of the gate, and always a bit higher in the middle and in this side. That's reflected by the performance of the zero-valent iron. We got occasional breakthrough on that side of the gate. Another date, a little bit earlier in the system, that's when we had these extremely high concentrations coming into the gate, hundreds of milligrams per liter of cis-DCE. Again, fairly consistent breakthroughs past the zero-valent iron, not unexpected given the treatment capacity, undesired given our design, of course. And the biosparge was not successful in removing those concentrations. So we still had hundreds of micrograms per liter of DCE coming through the system. Well, here's a table of some monitoring of the first row, which is just in front of the gate, and row 4 after the after the zero-valent iron zone. And we have 1, 2, 3, 4 dates. On July 31st, the concentrations coming into the gate were quite high. The concentrations going through the biosparge zone were failing our criteria. Concentrations had gone down a little bit on September the 30th, and the performance was somewhat better. On January 12th, concentrations were now down below the design level, and we got fairly good treatment. On April 3rd, concentrations had popped back up, and treatment wasn't again successful. One thing to note is that these concentrations are reported as less than the method detection limit. Because we were also trying to detect very high concentrations, the lab was unable to give us low method detection limits for those runs. So these method detection limits are well above the target concentrations. So while encouraging, they aren't yet evidence of adequate performance. So anytime the input concentration exceeded the design concentration, we had failure in the zero-valent iron wall. Here's a way to look at the biosparge zone, the concentrations at the front of the gate, entering the biosparge zone and leaving the biosparge zone. Again, the concentrations are in log units. You can see that at some times we got a fairly small decrease in concentrations in the biosparge zone. At low concentrations coming in, we got quite low concentrations coming out. Vinyl chloride especially seemed to be quite well treated. We believe most of that treatment was degradation because we again didn't see much coming out of the vapor above the bubbling water. So if we compare the overall treatment by looking at row 1 and row 8, the input-output, at different dates, we see that we got tremendous reductions all the time in all the target compounds. But when row 1 was high, row 8 was above our target concentration. When row 1 was within our treatment objectives or our treatment design, we seemed to work. Overall, if we look at our treatment objectives, we can see that in some cases we were perhaps meeting them. Again, our problem was our method detection limits were often a little bit higher than the California drinking water objective. But again, we got tremendous reduction in concentrations with this sequential reactive barrier system. So given that when concentrations were high coming into the gate, we had breakthrough. When concentrations were high on one side of the gate, the breakthrough occurred on that side of the gate. Our sense was there was really no mixing within the gate, no transverse mixing. So we would call this a non-mixing permeable reactive barrier. So my suggestion is it's very important to identify the maximum influent concentration to ensure that we would get adequate treatment with the zero-valent iron technology. The other observation we would make is that the construction, the dewatering of sand and removal and addition of material created significant hydraulic perturbations. And in fact, it's likely to take months, if not years, for those perturbations to dissipate. And if you were then going to establish how the system was performing, you may have to wait months or years before you can make that assessment. What other learnings did we come up with? Well, we determined that these sorts of PRBs really have no mixing capability. The zero-valent iron technology requires in-barrier reaction. There has to be contact between the water and the iron for the reaction to occur, so residence time is critical. We even had a 4 times conservative design, and it wasn't adequate. The concentrations coming in were far in excess of 4 times the design concentration. We did demonstrate that zero-valent iron, essentially a reductive technology, can be combined with an aerobic technology to give a sequential treatment. And our view was that if we were going to try this again in a real-world site, we would try to design some passive mixing in front of the zero-valent iron barrier. That is, we'd try and get the water circulating around within some zone just in front of the zero-valent iron to try and homogenize the concentrations. Then the average concentration coming into the gate would be the treatment design value. So that was our sequential reactive barrier in a very nice location, showing you that you can be quite innovative with the design of these systems, and that you can be unpleasantly surprised by inadequate understanding of concentrations before you come up with your design for the treatment system. Next time we'll talk about some more hydrocarbon type treatment systems. So until then, thank you and goodbye.